Today I'll be discussing on earthquake resistant design principles. I could have just said that earthquake resistant design. I could have just omitted the term principles. No, I wanted to make it very clear to you that when we go for earthquake resistant design methods, which are normally given in the code, before that we have to appreciate the principles. And if we can appreciate the principles, then you will be able to apply the earthquake resistant design methodology which are given in the different codes, and accordingly you can implement it. Because you have to understand the principles, then you have to make the design, then finally you have to develop the drawing, and that will be recommended for construction. So these are the steps normally we follow in case of earthquake resistant design. Now, before I go into the deeper part of it, try to understand few things which you can say the lessons from past earthquakes. These are the real photographs. Sometimes you will get it in the internet. And also, as I work with different organizations for your earthquake retrofitting and all these things, some photographs are also with me. I have just given few photographs. You see, it's a typical reinforcement concrete column. And at the base level, if the column hinge is formed, a stick hinge is formed, what does it mean? Means this particular section at the base level, it cannot carry any further moment. It cannot sustain any load. So, what kind of failure normally we observe in this particular situation? Just see, this is the kind of failure we observe. Okay. Now this is reinforcement of the column, but diagonal shear crack in the midspan of the column. Just at the midspan of the column is a diagonal shear crack. And why it is happening like that? How can we avoid all these things? All these things are, well understood by the engineers, researchers, and many things already recommended in the code. And by experience, the engineers also, they have understood how to handle this kind of situation. Ultimately, I don't think there is any problem in dealing with earthquake resistant design of RC systems or any other such. You see, this is another end, that diagonal shear cracking in the midspan of the column, but it's different type. It is different. Here you just see, here you just see. Both cracked, both are collapsed. Can't use this column again as it is. So, but this is also a kind of diagonal shear cracking. This is, you see, the shear and splice failure of longitudinal reinforcement. You can't see here, but you see, you know that when you are constructing the pile cap or even the shallow footing, you are rather taking the reinforcement from the foundation level and you are reaching to the ground level or slightly above the ground level, and then you lap your reinforcement, means the other piece of reinforcement is lapped with the this old reinforcement. Old reinforcement means which is coming from the foundation, and you continue. But if the lapping is not adequate, or sometimes you know that in different way we manage this kind of splicing situation. But if it is not done properly, then this kind of failure is generally observed. We will come in detail about it. This is say shear failure in captive columns, short columns. You see, there is a beam, there is another beam. In between, this column is there. Small, very small. Maybe below this beam, there is another column, but the length is short. Then what will happen? You know that the stiffness of a particular column, you generally calculate by, in many situations you are going for 12 bi by L cube. Right? The most important thing is that this L cube, that means if the L is less, then the stiffness will be very high. And if the stiffness is very high, then what will happen? That high stiffness zone will attract more forces. Naturally, when the more forces will be transferred in that high stiffness zone, and if the high stiffness zone is not designed for that force of the moment, then it will collapse. So that's why, you know, sometimes there is a tendency of engineers just to, you know, make some walls at the ground floor level or just providing a tie beam in between. And they think that if they can break the column length, make it shorter, they are making good for the structure. No. If they do like that, the stiffness of column will increase. 12 bi by L cube in cubical terms. So you just think. And when they are doing like this, then the column stiffness increases. It will attract more force. There will be a huge moment. And if the column is not reinforced accordingly, because this extra beam is given just before that, so whatever the column reinforcement available, if it is not sufficient, then there is a possibility of shear failure or any other kind of failure like this. Now you see this is shear flexure failure. That means there is a problem of shear. Let's suppose adequate stirrups are not there. But at the same time, there is no sufficient longitudinal bars. Then also this is possible. Then it is a shear flexure failure. Now, you see, this is another shear following column beam joints. It's very, very important. When you will be learning this in detail, and when you will be learning IS 13920 and how the column joints are to be detailed to achieve a certain level of ductility, then you will be able to appreciate better. But from this picture, you can easily see that the column beam joint suffered a lot and ultimately lead to shear failure. You see, this is generally, you see that during earthquake, the, the ground surface ruptures. And, nowadays through remote sensing, one can, monitor this kind of rupture. And they can also give you an idea about the maximum displacement during earthquake. I mean, on the width of the crack, maximum. And you all know that log base 10 of maximum crack width gives you an idea about Richter. So if the crack width is more, means it has undergone a very strong earthquake, right? So the surface rupture is a very, very important aspect. In code, in IS 1893 or any other code in earthquake, if you just go through the preface, generally people are not interested to go through preface, but if you go through that preface, then you will be able to understand that what kind of study they made after earthquake at a particular place. That means after earthquake, a group of persons, engineers, they're going to that site and they measure all these things. And ultimately, they can tell you that the intensity of earthquake in Richter, or like that, what type of earthquake it is. So many things they can tell you. So this code is basically based on this post-earthquake survey data. If you go through the code, you will be able to understand it. You see, some place, at some point of time, it was in zone 2. But later on, it is found that depending on the nature of earthquake, depending on post-earthquake survey, they could appreciate, no, it is not in zone 2, it is like zone 3. So it should be upgraded to zone 3. And accordingly, the seismic map is changed in IS 1893 code. So you have to understand this. Regularly, this zonation is upgraded. And at the same time, I can mentioning here that microjonation is also done depending on a particular situation, and that will give you site-specific seismic behavior of the ground. And from there, you will be able to find out many seismic parameters which are extremely helpful for calculating the base shear. See, this is another, probably it's a bridge pier, it's collapsed like this. you see cracking of the ground, huge cracking. Just think about it. The left ground which has ruptured like anything, cracking of the ground. And just after Bhuj earthquake, I got an assignment from a particular company in Kandla Economic Zone. It was a job of 300 crore, and there were 250 structures, and we had to classify these structures accordingly. We had to classify these structures depending on damage level, and then some structure is we recommended to demolish because you can't really go for retrofitting. It will be huge cost. Some are retrofitted, and some minor repair is sufficient. Was sufficient. So this kind of 250 structures were there, and I was the consultant in that project. Now the liquefaction. Liquefaction, you heard about it. I will discuss in detail in my future lecture regarding liquefaction. And depending on the soil property, during earthquake, the soil may lose its shear strength to a great extent. And just like a fluid. And if the soil below the foundation, if it liquefies, then what may happen? It may happen like this. This particular figure is taken from internet. See, the building is as it is. The building is as it is, first tilted. Like that. These buildings are not affected. This kind of, failure is normally observed in case of liquefaction. Right? I'll come in detail. Because previously liquefaction was not included in the code, IS 1893. But now it is included. And, I have included some numerical problems also and discussed about liquefaction in my recent book also. Now, what is the requirement of a building structure to resist earthquake forces so as to get reasonable serviceability? Try to understand. I am giving importance to reasonable serviceability at an optimum cost. That means, if you think that earthquake will take place and there will be no damage, absolutely it will be perfect. It will behave like elastic structure. No, in that case, the cost will be extremely high, and what you have to do, you have to accept a particular damage limit. That is, reasonable serviceability means everything should be within a particular limit so that it can be repaired. Suppose if the main frame of the structure is all right, everything is fine, but the walls are cracked. You can go for some kind of stitching and you can use the same wall again. So like that, but if it is beyond reasonable serviceability, then probably you have to demolish the entire structure. If you want to make it, damage-free structure, then it will be, you have to spend a lot. Even then, you can't ensure. There are many other aspects of secondary effects also. Now, these are the important aspects of earthquake. Structural configuration. Is it rectangular, L-shaped, circular, All these things are very important. U-shaped. Lateral stiffness, very, very important. The columns are providing major part of the lateral stiffness. Lateral strength. Stiffness is something, strength is something. Strength again related to the material. Then ductility, very, very important. The structure will not collapse immediately. Or even if, it undergoes huge deformation, huge cracking, still then, by seismic retrofitting, you can reuse this structure again. But whenever you are doing all these things, you can't deny aesthetics. You can't deny the functionality of the building, because that is totally, a subject of architects. So you have to talk to them, and finally you have to decide that, aesthetics, functionality, all these things are maintained as required, and mutually agreed, solutions. That is best. And for that, you have to choose the structural system in a most appropriate way. Structural system means it may be a totally different structure. It may be, French structure, and also, shear walls are there, right? So, I can tell you at least one thing, that whatever you do regarding structural system, you can choose in different ways. But you have to check the load path. How the load is transferred from the top to bottom and ultimately to foundation. If that load path is not proper, which we expect from a good building, then also you will be in deep trouble. The load path is also a very important aspect. A very, very important aspect. Now, the hysteresis model is extremely important to appreciate the strength and stiffness degradation, ductility, energy dissipation, capacity of the structure. You see, you heard about all these things in physics. When a particular structure is subjected to dynamic loading, right? At a particular point, at a particular time, maybe it is under tension. But immediately, in the next second, that particular point may be under compression. And that continues. So if the material is subjected to this kind of dynamic effects, then the strength of material decreases. Obviously, if there are cracks and all, stiffness will come down. And its post-yield behavior will change. And that will result to some level of ductility which may not be acceptable to you. The energy distribution capacity of structure. Whatever energy the loads, earthquake, wind, they want to transfer on the structure should be able to carry that amount of energy. It should not be disturbed. So that energy transfer part is also Very, very important. You see, RCC structure is not perfectly elastic even at the lower stress level. That all of you all know. It is concrete is not also, homogeneous, isotropic, elastic. No, but we are considering. In most of the situation, we consider strain diagram linear, and we also, you know, just uh, make an assumption that plane section before bending remains plane after bending, which leads to strain diagram linear, which is also not correct in case of concrete. But if you think about all these aspects, probably it will be difficult for you to analyze it. But if you can analyze the simple model, and after that, if you keep some kind of factor of safety, some kind of safety elements for this kind of structure, that will solve our purpose. So we will always try to go for the perfect analysis, but it is not always possible. At higher stress level, it undergoes cracking, etc. Stiffness of RCC elements will decrease appreciably, and deformation will increase drastically. But it will not collapse immediately if RCC structure made sufficient uptime. I just now I told you. But if the stiffness of structure element decreases, how much it has decreased? In recent code, they are saying that when you are going for earthquake analysis, then the beam stiffness should be reduced to a particular level. Column stiffness should be reduced to a particular level. I'm not mentioning the percentage that you know how much it is for IS 456. But regarding this particular aspect, different countries, different experts, they have got different opinion. And I think that in future code, this particular aspect will be given a lot of importance, and some detailed understanding can be made about it. And accordingly, analysis will be correct. Because there are many questions are there, but which I don't want to discuss now, because you have to first appreciate the subject, and then slowly when we go in detail of the subject, then I'll be able, if I discuss these things, then you'll be able to appreciate that what kind of change is required even in the recent code. Total energy level of ductile RCC structure should be very high. If the material or even the structure is ductile, that means that area under the curve, that is the total energy. If it is ductile, actually the total energy level will be very high. Ultimately, design will be reasonable, economic, ensuring less damage, as well as safety of the structure. At the moment you are accepting the post-spill behavior, you are accepting cracking to some extent. Reduction of ductility also you are accepting to some extent. Secondary cracking in the walls, you are accepting it. And that's why I told you that the structure should be designed with reasonable serviceability to ensure, or to avoid collapse. There should be any collapse. We don't want collapse. Little bit of, acceptance in serviceability, yes, that is, we can accept. we will repair it later on. But we don't want that column beam will collapse. No. Then what are we doing? Now, redundancy of the structural system is not dependent concept and has an indirect effect on ductility. Think about it. Just think about it. It's a very important topic in research still now. Very less contribution. You see, if you just have a structure with 4 columns and a slab on top of that, and if you have a structure of 100 columns and there are many slab panels, not only 1 story, maybe 5 stories, 10 stories, then redundancy level is increasing. When the redundancy level is increasing, then just think about it, that in a redundant structure, when a particular joint, suppose the plastic hinge is formed, what will happen next to that particular? There will be redistribution of forces. There will be redistribution of moments, which you normally observe in plastic analysis. If it is redundant, then you can easily imagine that how it will happen. It's a very important aspect. It's sequential failure. So if somebody has an idea about sequential failure, and accordingly he has got an idea about ductility, obviously a connected plastic analysis, then only he will be giving you exact recommendation. The only thing I must tell you that response reduction factor, that for ordinary moment resisting frame, you are considering 3. But for specially moment resisting frame, you are considering 5. So when you are considering 3, then the base shear is more. When you are considering 5, then the base shear is less. Why are you considering like this, 3 and 5? It is based on redundancy and ductility and many other aspects. This is also an area where I have given some idea in my book. Redundancy of structure need to be understood to appreciate the sequence of failure and to assess overall ductility of the structure. What is overall ductility of the structure? Suppose a tall building frame is here. During earthquake or during any force, the maximum displacement is expected to occur at the top level. Now, if you have this load versus displacement behavior or load versus tip displacement, that particular response, if you have that, then the displacement when yielding just started and displacement at failure stage. Displacement at failure stage is much more. Of course, it depends that how you are defining the failure stage. Is it critical collapse or before that or something? But anyway, the displacement at failure stage by displacement at the yielding stage, that means just after elastic stage, this ratio is nothing but ductility ratio. Now for a building in different codes, you may find that they are sometimes expecting 3, sometimes 5, or in many structures, even they allow more. Similar thing, similar kind of expectation from individual beams and columns. I mean, individual beam also, if you find out the ductility ratio, some codes are expecting 10, some 12, some 15, like that. So already we can assess the ductility to some extent by calculating ductility ratio. So that is very important. And when you are trying to find out the displacement at the failure stage means the way you have defined the failure stage at that stage. Then the sequential failure playing a major role, and redundancy is also playing a major role. And if you can increase the ductility ratio, obviously the response reduction factor may be increased, and you can reduce the base shear. So they are interconnected. I'll come to that. But at this stage, I think we should appreciate at least this comments. The stability of the building is affected mostly failure of the column rather than the failure of beams. Therefore, it is better to make beams as weak ductile links than columns. This concept known as strong beam, weak beam. This is the most important concept in earthquake resistant design. The strong column should be as strong as possible. Comparatively, beam may be weak. Weak doesn't mean that it will collapse. Right? But the stiffness of the column will be very high compared to stiffness of beams. And that is which is followed in different way in the design methods given in IS 13920. Right? So when we go into detail of those things, calculation and all these things, then you'll be able to appreciate better. Now the core concrete. What does it mean? Core concrete means that when, suppose there is a column, there are suppose 16 longitudinal bars. Within these 16 longitudinal bars, the inside part is known as the core. That is the core concrete. Similarly for beam, the inside part within this stirrup, the inside part, that is core. The core concrete is prevented from dilating in the transverse direction and thereby enhancing the peak strength and ultimate strength capacity. You have to prevent the core concrete from dilating. How we can do it? You can just provide stirrups very closely. Use of closer stirrups in beams or closer spacing of lateral ties makes confining pressure more uniform and effective. And the dilation is, prevented. So, in a particular beam, suppose the spacing is 200 centimeters. And if you consider another beam, same cross section, same thing, same longitudinal reinforcement, But only stirrup spacing is 100 centimeters. You can expect higher ductility where the stirrup spacing is 100 centimeters. Why? Because it has prevented the core concrete from dilation. And it provides more uniform pressure and effect. As a result, if you go for an experiment also, you will be observing higher ductility where the spacing of stirrups is less. Spacing of lateral type is less. Then you can expect higher ductility from the column. And that's why, in slowly you will understand that in IS 13920, in many situations they are recommending the stirrup spacing only 75 millimeter near the junction of beam and columns. Just to prevent dilation at that particular joint. And just to improve the ductility of the joint. And as a result, the ductility of the entire structure will be better. The ductility of joints are better. Obviously, the ductility of the entire structure will be better. So this is the way you have to think. Finally, the level of ductility of building structures or structure is obtained by applying pushover analysis. It is there in your IS 456. And this pushover analysis is very, very, very important. You see, I was talking about the sequential failure and all these things, rusting information, all these things. So, pushover analysis will be able to take care of those things. Now, so far as dynamic behavior of the structure, it is desirable to have a pure translation mode as the lower modes of vibration and push other modes to the higher level. So you have to be very careful about lower modes of vibration. Then automatically the higher modes of vibration will not create or give you trouble. More you will be dealing with dynamics of structure, you will be able to appreciate this. That which one is pushing which mode and why that is required. Okay. So dynamics, it's not much mathematics. But if you can play with it, you will be able to come up with many, many things. And that will ultimately help you in analyzing the structure or designing the structure. Correct assessment of time period is extremely important. That you can easily understand. If the time period is not assessed properly, then your SA by G will be wrong. If your SA by G is wrong, then your base shear is wrong. Then the entire analysis is wrong, design is wrong. So time period assessment is extremely important when you are dealing with code. When you are dealing with code, you are not always going for actual analysis. You don't bother about code. No. Unless you know the correct time period, you won't get SA by G. And that SA by G depends on the type of soil, that particular curve. And when code is recommending something, some curve for soft soil, hard soil, medium soil, yes, you can use it. But those curves also have some limitations that when I'll discuss microgeneration in detail, then you will be able to appreciate. That's why in many situations we don't use the those curves which are in the code. Rather, we develop those curves by microgeometry analysis. Okay, that is another subject. Even the soil mechanics people, they are also dealing with this. Mostly they are dealing with this. Now you see the few horizontal irregularities. You see, normally in earthquake, you see, not normally, the earthquake force is acting at the mass of center of the mass. Earthquake force and inertia force acting at the center of mass. But that center of mass may not coincide with center of gravity. It may not coincide. As a result, what will happen? On plan, the earthquake force is hitting at the center of mass, which is a distance away from the center of gravity. So there will be a moment on plan. And there will be huge torsional effect on the building. That is to be taken care of if this happens. How to take care of this thing? Obviously, I will tell you in my future lectures. Re-entrant corners. What is this? What is the advantage of this? Diaphragm discontinuity. What is happening? Out of plane offsets, non-parallel systems. This, I have to discuss all these things in detail, showing you the pictures in sketches. Then you will be able to appreciate. But these are the, just I'm telling you, these are the important aspects. If anybody asks you about it, if you mention all these five, and if you are in a position to explain them properly, then that person will be happy. That's my point. So that's why now we are discussing our principles. Later on, we will discuss these aspects in detail. The twist about the center of stiffness takes place. If the center of mass of the building is not coinciding with the center of stiffness, and this affects furthermost column Y, because if there is a torsion on a particular plane, the extreme column will be undergoing huge stresses. PR by J. Stress due to torsional movement is PR by J, where R is the distance from the center of gravity. Okay. So the furthermost column from the center of stiffness means center of gravity, most severely affected. Of course, the other columns will be affected, but the peripheral columns, they are severely affected. Now you think about the vertical irregularity. A building is uniform. No, it is not like that. At least in last day I have shown you several buildings which are not vertically regular. Abrupt change in floor plan. Column of a particular floor level more flexible. Suppose column size is same, but in between one floor is not there. Obviously that in that particular zone, the column will be extremely flexible. It may be weaker than the above floor. Yes. Top story. Very good. You know it. Short column I have discussed. Discontinuous and offset structural walls. It also creates problem. A particular floor significantly heavier than the adjacent floor. Suppose in a particular floor you are using for a particular purpose, the load is very high. Compared to the adjacent floor. That will problem create problem regarding this eccentric loading effect. Now you see, there are four virtues of earthquake resistant buildings. If you go through any book, they will always tell you about these four virtues. One is overall geometry, then the structural elements, whether it is a moment resting frame or it is having shear wall, and the significant non-structural elements, facade and all this. These are important things. The three aspects should be discussed before you finalize the, or if you even if you start designing the building. These are very, very important. Right? Now see this architectural consideration in the overall size, shape, geometry, obviously size of the building, horizontal layout of the building, vertical layout, adjacency of the building. All these things are important. What is the distance between two buildings? Adjacency of the building means what is the distance between two buildings. If they are very close to each other, what will happen? Not my point. So these are the basic aspects. Just think about it. One building is too tall. One is too large in plan. One is too long. Right? In tall buildings with large height to base size ratio, the horizontal movement of the floor during ground setting is large. In buildings with large plan area, like warehouse, the horizontal seismic force will be excessive, to be carried out by the columns, and you have to assess accordingly. Don't take it casually. Too long. That is also not good. So all these things you have to be careful of it. You think about a building like this. A building may be, rectangular one. Good. We accept it. Circular one, it's good. No problem. But the moment it is, T-type or a curved one, then, there is problem. Center of mass and center of gravity will not coincide. If it is a L-type, then also so many things will happen, but you can separate like this. You can make it into two blocks. And between the blocks, you can manage with different types of connections. You can provide water bars and other materials. And you will find that the seismic behavior of these two buildings will be better than if it is a L building. So this kind of separation helps you a lot. Now, try to think about this kind of buildings. A building with vertical setback. Building that have fewer columns or walls in a particular story. Building on slope ground, which is happening in hilly areas, having unequal columns. Building with floating columns. Suddenly a particular column started by a particular level. So that's not good. So you know these figures, from the figures, you can see that what kind of setback systems are there. So you can't, these are not at all recommended. Just think the weak or flexible story. The ground floor columns are extremely flexible, and if you compare with the columns of the upper floor, the ground floor columns are extremely weak. So in between the floors, if the stiffness of the column changes to a great extent, that is also not good under earthquake. The other one is the right one. They are extended the beams and then they start constructing the column underneath. These are also not good. These are also not at all good for seismic situation. Now, you see, if these buildings are very close to each other, what will happen? During earthquake, both the beams will vibrate and there will be pounding effect. One building will hit the other building. And that is quite a high, force. If you want to calculate that force, you can calculate it. So either you have to go for a reasonably higher gap to avoid pounding effect, or you have to take care of the pounding effect and the extra forces for that. Or you may just simply join them to, if the relationship between the owners of two buildings is good, then sometimes. But anyway, these are the many issues are there, whether the buildings are already constructed or not, what is the municipal rule, right? But this pounding effect should be avoided. Now, this is totally a different aspect, and try to understand it properly. Try to understand it properly. This is your stiffness is increasing. Strength is increasing. Okay. And this is that ductility ratio we are studying. The displacement at this level, the displacement at failure. Ratio is ductility ratio. So when we are discussing about stiffness and ductility together, right? These are the overall properties. You can't say that this is important, more important than other. No, you can't say. They are interrelated. Lateral stiffness refers to the initial stiffnesses of the building, even though stiffness of the building reduces with increasing damage, which I was telling you. Lateral strain refers to the maximum resistance of the building offers during its entire history of resistance to deformation, relative deformation. Ductility towards lateral deformation refers to the idealized ratio of maximum deformation and the idealized yield deformation. More is the ratio, better. The maximum deformation corresponds to the the maximum deformation sustained by it. There is a percentage I just quoted there. I'm not giving more emphasis to the 85% or like that. It changes time frame, but it is just like that. Okay, so you have to be very careful while designing it. Now you see, if the building is, you know, it's just a perfectly elastic building, and it is like this, straight. It is just straight. It is ideal. But practically, it is like this. Why? After a particular point, you are allowing the post-steel deformations. You are allowing the building frame to crack. You are allowing the nonlinear behavior. Right? And in this way, you are really gaining huge energy, which is just required for the building. Of course, the serviceability limits are also given. Not that any amount of displacement is allowed. Beyond a particular displacement, you may not allow. But if you go like this is a linear behavior. It is not practical. So ultimately, we have considered this. You can do it. Theoretically, everything is possible. Now I'm just reading out this thing. Okay. Earthquake shaking is most severe because it imposes displacement under the building, which is time varying. This is in turn demands lateral deformation in the building between its base and the upper elevations. Higher is the seismic zone, larger is severity of this imposed relative displacement. Building should be able to withstand the imposed deformation with damage, mind it, with damage, under small intensity of shaking and with no collapse under high intensity of shaking. Plus, the building needs to possess large inelastic deformation capacity and needs to have the strength in all the members to sustain the forces and moment in this fluid. That means it should be ductile. We will not discourage inelastic behavior, but under any circumstances, we will not accept any collapse of any beam, any column individually, or the building as a whole. So double demand in buildings subjected to earthquake effects needs large inelastic deformation capacity in the building and need to sustain the induced forces. This you have to keep it in mind. Right? You see, later on, sometime I will discuss capacity-based design. Then there you will find that this kind of concept which we are, this kind of principles which we are discussing will play a major role there. Now design measurement. Method of design of building should take care into account of the deformation demand of the building and the deformation capacity of the building. Capacity and demand. The demand on the building depends on seismotectonic setting of the location of the building, but deformation capacity of the building is within the control of design professionals. First one is not controlled by you. Second one, you can control. The concern is that both these quantities have uncertainties. Yes, they are dependent on time. You are not sure what is happening. On one hand, even though some understanding is available on maximum possible ground displacement at a location, earth scientists are not able to clearly provide the upper bound of these numbers. They will give you some idea, but they can't give you the maximum like that. Each new damages earthquake has always provided surprise. That is true. Because whenever something happened in a particular place where already earthquake took place few years back, and we are getting different results. And on the other hand, analytical tools are not available to estimate precisely the overall nonlinear behavior of the structure and its ultimate deformation capacity. So you can easily understand the real challenge. It is not only your mathematics or physics or whatever you're doing. You are dealing in a natural force which cannot be predicted properly. But even then you have to do something so that even something happened which you never anticipated, but the structure will not collapse. Right? So this is the kind of thing, these structural engineers are continuously working on it. And they are suggesting in the code. And ultimately, in many situations, you found that the building has not collapsed. If you have designed correctly using IS codes or other good codes. I tell you, I have designed a building in Andaman, tall building. And you can easily understand that, the Andaman is very active, like Indonesia. A few years back, few means that also maybe 10, 12 years, I forgot. One day, the earthquake occurred there, severe earthquake, and I just saw in the newspaper, but within 5 minutes I got a call from Andaman. My client was telling me, sir, what the building you have designed here, it is perfectly all right. I told them that, see, I have not designed anything extra. I have only followed the code strictly. So, the same experience I had when I visited the Bhuj after earthquake. That many small buildings are collapsing under earthquake, but many high-rise buildings are perfectly all right. Even after earthquake, with little bit of repair, they can reuse it. They can stay there. So that is why, whatever experience we have, whatever factor 50, whatever it is, everything is considered together, and ultimately they have recommended in the code, in IS 13926, IS 13920, IS 4026, IS 1893. So you have to understand these codes clearly. And accordingly, if you do the design, applying little bit of your knowledge in structural behavior under dynamic forces, I think, I think in most of the situations we will win. Unless it is totally different what you expected. For that nobody will blame you because you didn't have data. What can be done? Right? So you see, this is just see a typical seismograph I have taken from this encyclopedia Britannia. You see, this is the acceleration and time. This is if you convert it to velocity, it is like this. If you convert it to displacement, time, it is like this. So if you have this, means you have this also. If you have this, means you have this also. So we try to measure this during earthquake by implanting some, instruments at different levels from ground level in the soil, and we continuously get the response from those instruments which we are recording in the computer. Later on, people are using it for analysis. And this kind of systems are, are extensively used in IIT Roorkee. And nearby locations are, implanted with instruments. Because the government has given them money to do this kind of research in detail, separate department, like that. Okay? But this is important. You see, this is you all know that this is the typical curve you are using to get your seismic acceleration. Right? Obviously, seismic acceleration means it ultimately gives you the best shear. And if it gives you the best shear, then the best shear divided by the vertical load will give you something. And this is the time period. So just this ratio, the time period, similar kind of curve, same kind. But they are related. Just think about it. If your prediction of natural period is wrong, then what will happen? If you are predicting here, it is something. If you are predicting here, it is something. So don't just consider it just a problem you are solving. That is for your examination. You will be wrong. You will be getting part marks. But if it is in really wrong, then obviously your design will be wrong. And this is like anything. But be very careful. Those who have not yet attended industry, you are only considering the performance in the examination. But those who have already worked in the industry, they know if there is something wrong from your design, then you will be in deep trouble. People will ask you many things and you have to answer. If it is not done, then you have to correct it. So be very careful. Don't take it casually. Now you just see this is the kind of building, small building, slightly higher, slightly tall. The slender building, very slender building. And your naturally time period will increase. More people will increase. More flexible. Okay. So this is the effect of building height. Obviously not building height, it is slenderness issue. Okay. Same plan area, building height is increasing. That is what I have shown here. This is another thing, is very important. Suppose you have designed by orienting the columns like this. Okay, longer side this way and shorter side along y-axis. Okay, more or less square suppose. And somebody is making it more rectangular. Here it is 400 by 400 square almost. And here it is 550 by 300 in rectangular. Another person, it has just change the direction. You see the time period is changing. Right? So the orientation of column is very important. That means if a building is rectangular, suppose 15 by 30, then building is weaker along 15 meters. The building is weaker along 15 meters. So how you have to orient the column? You have to place the longer dimension of the column along 15 meters, shorter direction of the building. That means if you want to provide a 300 by 500 column, then 300 will be along that 15 meter and 500 will be along 15 meter and 300 will be along 30 meter. So you have to provide the larger dimension of the column along the weaker side of the building. 15 by 30 means obviously the building is weak along 15 meters. What's my point? And with the change in time period, your SI by G will change. What's my point? Think about it. You see, these are the buildings, the unreinforced masonry infill buildings. Okay. This curve is, for buildings with unreinforced masonry infills. And this is for your buildings without unreinforced infills. There are some other cases also. I'll give you all these things. Then you'll be able to understand that why these things are so important. Because everywhere the fundamental period is involved. And that is related to the base shear. And that affects the design to a great extent. You see, this is if you consider the stiffness of the entire column, gross stiffness, and if you consider the crack stiffness, see how the time period is changing. How the time period is changing. For different types of building. This is very slender building. Difference is very high. You see, this is the kind of thing, I was talking to you that the building may shift this way, it may shift this way, it may be in the torsional mode. Right? Bending of the column may be like this, or normally like this. So all these aspects, people are not really thinking in detail. And that's why sometimes it happens that even if they have worked hard, but even then there is something wrong and the building suffers a lot. So you see the principal causes of damage: soft story, floating column, poor quality of material, then faulty construction practice, pounding effect, I told you, adjustment, inadequate ductility, These are the things you have to be very, very sure about. Thank you very much for today.